Hello and welcome to this lecture on T-Test. My name is Brian Miller and I'll be guiding you through this tutorial. Bear in mind that T-Tests are appropriate for when you only have two different groups compared on some continuously measured other variable. Let's get started. Well, what do you know? The crowd goes nuts. Once upon a time, there was a chemist named William Gossett who worked for the Guinness Brewery in Dublin, Ireland. Gossett had been hired to apply biochemistry and statistics to Guinness's industrial processes. He devised the T-test as a way to monitor the quality of stout. The T-test work was submitted to and accepted in the journal Biometrica and published in 1908. By the way, it is still a premier journal. Company policy at Guinness forbade its chemists from publishing their findings. So Gossett published his statistical work under the pseudonym or the pen name of Student. Guinness had a policy of allowing technical staff to take leave for study, which Gossett used during 1906 and 7, where he studied in Carl Pearson's biometric laboratory at University College London. Of course, Gossett's identity was then known to fellow statisticians and to the editor-in-chief of the biometrical journal, Carl Pearson. Yes, that Pearson, as in the Pearson product-moment correlation. That's why, and all of this is why, the T-test is sometimes called Student's T-test. Small world, huh? Let's move on. Well, what is a T-test? Well, the common definition is simply comparing two means, two average scores, to see if they are statistically significantly different from each other. The technical definition is any statistical test that uses the T family of distributions. What? A family? Okay, let's move on. T distributions. You cannot assume that a T-distribution is a nicely shaped so-called bell curve. It's not all perfectly standard normal distribution. You cannot use probabilities based on the normal distribution if the population standard deviation is unknown, which it almost always is, or we have a small sample. So when the sample size is less than 100, the shape of the T-distribution will differ from that of a Z-distribution. Once you have about 100 subjects in your sample, the Z-score and T-score are interchangeable. So this is the family of T-distributions that were created in order to take sample size into account, and it looks like this. So we see here a difference in kurtosis on these distributions. With degrees of freedom equal 1, the yellow curve, it's more platykurtic than is degrees of freedom 2, which is more platykurtic than is degrees of freedom 5, all the way up to degrees of freedom equal infinity. Okay, let's move on. The independent samples T-test. This is the most commonly used T-test that there is. We'll cover a couple of different sorts of T-test later. In this one, we're comparing the means of two independent samples on some given variable. Independent. Independent means that members of one sample are not a member of the other sample. The IV, the independent variable, the antecedent is dichotomous. Dichotomous being a special case of categorical or nominal where there are only two different categories. You cannot be a member of both samples at the same time. The samples are independent, and the variable on which you're being compared, the DV, is continuous. That is, it's measured either interval or ratio. Well, here's an example. We can compare the average level of self-esteem of randomly selected men to that of randomly selected women. Well, the IV here, the dichotomous variable here, is sex. And that can be coded as 0 and 1. It can be coded as -5 and 214.7. It doesn't really matter because these numbers are just names, numeric names for the nominal variable. And in this case, of course, the IV is self-esteem, usually coded using a Likert response scale. 1 to 5, 1 to 7, 1 to 9, a numeric response scale, 1 to 10, something like that. Some variable that is coded continuously. Let's move on. So the difference in group means between these two samples could look like this. So we have the red distribution. We have X bar sub 1. X bar is the mean score in sample 1. X bar sub 2 is the mean score in sample 2. And we see that they're both normally distributed, and there is some distance, some difference between the mean scores in these two independent samples. You also see that there's a substantial area at the very bottom, down in here, hope you're looking at your screen, that overlaps. This does not mean that you can be in one group or the other. It just means that there are people in the green group who have really low scores, and there are people in the red group who have really high scores. The question is this difference likely to be non-zero in the population? If this is truly a randomly selected sample from the population to which it is hoped to be generalized, and the sample sizes are large enough, and some other things which we'll cover in a little while, this could be a meaningful difference. Meaningful being slightly different than statistical. A statistically significant difference is something we'll discuss in a little bit. Let's move on. So here's the model of the hypothesized relationship. So I've put sex into a rectangle because it is an observed characteristic. You could take a DNA test, XX, XY, that's your sex. Self-esteem is a latent variable, so that's placed into an oval or an ellipse here. Well, we're saying, in essence, that sex causes self-esteem. Now, I don't know what the hypothesis is necessarily, that maleness causes higher self-esteem or femaleness, etc. But we're saying here that there is a relationship between sex and self-esteem, between biological sex and self-esteem. That's what we're hypothesizing. This important modeled relationship will become very, very important once we get into correlations, which, side note, a t-test is just a point by serial correlation. They're exactly the same thing. Anyway, let's don't get ahead of ourselves, but let's move on. So here are some hypotheses. So the null hypothesis is that there's no difference on this DV on self-esteem. And it can be noted as mu. This is the Greek character mu for a population. Greek letters indicate population parameters. Roman or Latin letters indicate statistical samples. Okay, so we have mu sub 1 is equal to mu sub 2. No difference. Similarly, you could write it as mu sub 1 minus mu sub 2 equals 0. Same thing. In order for 0 to be correct, both mu sub 1 must be the same as mu sub 2. So this is the null hypothesis to which statistical tests are applied. But we really kind of think of hypotheses more in their alternative format. So here we would say men and women differ in self-esteem, okay? Simply that the mu sub 1 is not equal to mu sub 2. Or alternatively, mu sub 1 minus mu sub 2 is not equal to 0, okay? We tend to think of hypotheses in alternative formats, but we actually test hypotheses by testing the null hypothesis format. Let's move on. All right, here are some of the assumptions of the independent sample t-test. All of these statistical tests have a certain set of assumptions. Violations to assumptions can sometimes make the use of that test completely inappropriate. However, most of the tests subsumed in the general linear model, for example, t-test, ANOVA, ANCOVA, MANOVA, MANCOVA, correlation, regression, canonical correlation, etc., most of those things are fairly robust to violations of the assumptions. All right, so one assumption of the independent samples t-test is that, as we've already mentioned, one variable must be categorical and the other variable must be continuous. That is, one variable is categorical and one is continuous. Group membership is exclusive and unrelated. So the previous example, you're either in the category of females or males. The scores are normally distributed. That is, the self-esteem scores are normally distributed in both samples. Not just one, but both. And the samples are similar in size. And there is a similar variance of the distribution of the scores. This is called the homogeneity of variance assumption. It simply means that the spread in each sample around their respective means is similarly wide. A very, very narrow leptokurtic distribution for females and a very, very wide platykurtic distribution for males will likely be a violation of the homogeneity of variance. That is, the variances are not homogeneous. There are ways of overcoming that, called the Levine's test, will tell you if they are actually significantly different, and then there's an adjustment to the degrees of freedom, but that's beyond the scope of this. Let's move on. All right, conceptual issues. Basically, is the observed difference between the two samples large relative to the standard error of the difference between the means? So the general, and this will become more clear to you as we walk through it, so be patient. The general formula is as follows. T, we will calculate a T score, a T value for a T test. They all mean the same thing. T is equal to the observed difference between the sample means divided by the standard error of the difference between the means. Or it looks something like this. X bar sub 1 minus X bar sub 2. That's the observed difference between the sample means. The denominator is a little bit more complex. That's the standard error of the difference between the means. But, I have a separate slide on that. Let's move on. The standard error of the difference between independent sample means. The definition of this is that it's the average expected difference between any two sample means on a given variable when those samples are randomly selected from two populations. So sampling error can play a role here. If the samples are randomly selected, then we're looking at the average expected difference between them. Anytime you see the word standard, think of average. A standard deviation is just an average deviation or an average distance of an observation from the mean. The standard error is a little bit more complicated. Here's an example. So, when comparing men and women's levels of self-esteem, the standard error is the average amount of the difference on this variable. Now, that we would expect to find between any two randomly selected samples from larger populations. So if we're using truly random sampling, any sample from females and any sample from males would be sufficient. And here's the formula in a little bit greater depth. So the standard error of the difference is the square root of the variance of scores on X bar sub 1 plus the variance of scores on X bar sub 2. Now the little blue boxes at the bottom say S sub x bar 1 is the standard error of the mean. But here it's squared under the square root. It's squared plus squared, and then you take the square root of that to get it back into the original metric. And you're probably glazing over at this point in time, but stick with me. We're going to understand it. Let's move on. Statistical significance. I alluded to this earlier. Is the difference meaningful, or is it statistically significantly different? So finding significance is finding the probability of getting a t-value of a certain size by chance. So if you have t equals 4.178, I just picked that out of the air. P less than 0.05, that means that there is a less than 5% chance that other samples randomly selected from those two populations would result in a zero difference. In other words, there's almost like a 95% chance that this is not chance. There's a 95% chance that another randomly selected sample of females and another randomly selected sample of males would also be different. Now you have to take into account the sample size via degrees of freedom, because the shape of the distribution, as I showed you earlier, changes as your sample sizes change. So when this shape distribution changes, the probabilities associated with it also change. So to find the degrees of freedom for an independent samples t-test, you add the two sample sizes together and subtract 2. And it looks like this. Degrees of freedom, independent sample size 1 plus independent sample size 2 minus 2 equals the degrees of freedom. This is going to be critical when you look up a t-score in a table, that you know what the degrees of freedom are. Now, most modern software packages will do it for you. If you want to go old school, you can do that too. Let's move on. Okay, as I alluded to earlier, there are other types of t-test. Other than just the independent samples t-test, there is a dependent samples t-test. This is just essentially a repeated measures test. We're trying to determine if a change over time on the same sample is statistically significant, that is non-zero. So the example here is, does self-esteem increase after earning an A in stats class? It might for some, okay? The key here, the dependent samples, is that the sample is the exact same sample at time 1 as it is at time 2. The independent samples t-test is two different, completely different independent samples comparing the means. Here we compare the mean of a particular sample at time 1 to its mean of the same sample at time 2. We also have a one sample t-test. So this measures if the mean of a group of subjects is simply different from some predetermined value. So for example, are stat students smarter than average? That is their IQ different from 100? We can plug into the formula 100 and determine whether or not the sample mean of the observed subjects is different from that. Now, as we'll find out when we get into multiple regression, the statistical significance test of a regression coefficient is technically a t-test, a one sample t-test, where that coefficient, its score, its magnitude, is compared to 0. Let's not get ahead of ourselves too much, but let's move on. Okay, so here we're going to go through an example of conducting a t-test by hand. Now remember this formula. When we looked at it the first time, we remember that the denominator it's a mess, okay? But we can do this math real simply in our heads. We can do this. So we'll use this formula. And the stuff we'll need for calculation would be the information from the data from the samples. So let's say we have 21 managers in a sample and they score 16.5 on some test. I don't know, mechanical comprehension ability, something, typing, whatever. 21 managers score 16.5. That's the average score of 21 managers. Some likely scored a lot lower and some likely scored a lot higher, but this is the mean score. The standard deviation is 2.1. That means that 95% of the particular subjects are between 4.2 above and below the mean. Anyway, the other sample has 14 subordinates. They score 12.2 on the same test, and their standard deviation is 2.6. So first we're going to find that pesky, complicated denominator, the pooled estimate of the standard error. Every statistical test has in its denominator some sort of standard error, some sort of average amount of error. In this case, we're trying to find out if the difference between these two samples is large relative to the amount of error. Hopefully it is. We'll substitute these values into the t-score formula. So let's move on. All right, so this is calculating the pooled estimate of the standard error. So down below it, we have s squared sub 1. It's actually s squared sub 1. The 1 and the 2 are kind of in the wrong place here. Is the variance of group 1. The s squared sub 2 is the variance of group 2. N sub 1 is the sample size of group 1. N sub 2 is the sample size of group 2. We can plug and chug what we know from the last slide into this. Let's move on. So here's that formula again, and now we're going to plug and chug. All right. The sample size for the managers is 21. N sub 1 minus 1 is 20 down here in the lower formula. The standard deviation for the managers is 2.1, so S squared is 2.1 squared. The sample size for the subordinates is 14, so N sub 2 minus 1 is 13, times the standard deviation squared, which is the variance, S sub 2 squared, 2.6 squared, okay? Now this stuff over to the right, this is the sample size weighting mechanism for when the samples are different sized. If they are the same exact size or a very similar size, this last parenthetical expression is not really even needed. And then 33 would be the sample size of 1 plus the sample size of 2 minus 2. So we have 21 plus 14 minus 2 equals 33. We can solve. Ta-da! 0.797. That's the pooled standard error of the difference. Now we're going to plug these scores into this formula. Remember, 0.797 will go in the denominator, and the means go in the, was this right? Yes, and the mean scores, x bar sub 1 is 16.5 minus x bar sub 2, 12.2. So we can plug and chug that a little bit. 4.3 divided by 0.797. 5.395. That's the t-score, the t-value. The t-test is equal to 5.395. Well, that doesn't mean very much to us. We don't know if that's big or small or what. Next, we have to calculate the degrees of freedom. That's going to be n minus k, where n is the sum of the sample size in both groups, and k is the number of groups. That's always going to be a 2 in a t-test. K is always equal to 2 in a t-test because there's always two groups. So the degrees of freedom here is equal to 33. All right, so we have a t-value of 5.395 and degrees of freedom of 33. So we can look up the critical value for the t-score in a statistics table like this one on the screen, or like any that are in any statistics book. Sometimes we have to interpolate between the values in here. If you can see this, you see degrees of freedom goes 27, 28, 29, 30, 40, 60, 120. All of those would require some interpolation here because we have degrees of freedom of 33. So the critical value in this table is approximately 2.03 with a statistical significance value of p less than 0.05. Because our calculated value of 5.395 is larger than 2.03, this test is indeed significant at p less than 0.05. In fact, it's such a large t-value, it's also significant at p less than 0.01 and p less than 0.001, which means there's a 1% chance that samples, no, there's a 1 in 1,000 chances that this value is a result of chance alone. Yay! Let's move on. Well, what do you know? Thanks. That's all for now.